Welcome back. Now, in this video, we are going to learn about single sample proportion test. This constitutes part 3. We will be also computing some problems on large samples. Learning objectives: to perform the testing of population proportion for a large sample, to understand the relationship between testing of mean and testing of proportion, to implement the testing procedure in real life problems, to take decision on accepting or rejecting H. We consider a population of units, each of which can be assigned any one of two values of a factor. We consider factors which are dichotomous, that is, the number of values assumed by this variable is only 2. These values are also called categories or levels. I give a table. First column describes some factors, second column corresponding levels for each factor. For instance, 6 you can have two categories, male and female. A finished product may be defective and non-defective. Disease: a person can be infected or not infected. Conventionally, the levels are coded by numerical values. One level is selected as the base one and assigned a value 0, and the other one is coded as 1. For items, a non-defective category may be assigned 0 value and the defective category may be assigned 1. For the factor 6, the male category may be assigned 0 and the female 1. This is not just for convenience, there is a statistical advantage. The advantage of numerical coding is shown here. Let the population units be sequentially numbered for identification. You look at the table, the top row units are indicated, second column onwards U1, U2, U3, U4, U5. I have taken only 5 sampling 5 units, they are given 1, 2, 3, 4, 5. The category, they could be male or female, third one male, fourth one male, fifth one female. The number of males equal to 3. So, just counting the males I can find this value, but if I code for male 1, female 0, then for the first unit 1, we have the code 1, for second unit 0, for third unit 1, fourth unit 1 and so on. Now, number of ones is 0 is 3. These two rows do not convey any other information, but what is the mathematical convenience? Now, I am going to introduce a new variable I call coded variable. X 1 is assigned for U 1, x 2 is assigned for U 2, x 3 assigned for U 3 and so on, and these x 1, x 2 are taking 1 for male, 0 for female. In case of manufactured products, the items may be defective or non-defective. They may be coded respectively as 1 and 0. If x I denote the coded variable for ith unit, that is x I takes value 1 if the unit is defective, 0 otherwise, then the number of defective units is sigma I over x I. Hence, the number of variables taking value 1 can be obtained by summing the dichotomous variable x I. What is the advantage? The ratio of number of males to the population is a fraction, also called as proportion. This is denoted by phi, where phi equal to ratio number of males divided by total number of units. Mathematically, this is equal to sigma x I summation over I divided by the total number n, we denote by mu. This proportion is equal to the mean of the population. By coding a units taking a dichotomous variable and summing, we get the mean of the population. So, this is the idea connecting the mean and proportion. Hence, we can apply the methods of testing the population mean to the testing of population proportion. For this, we deduce the sampling distribution of proportion. The sample proportion is denoted by P. Using the analogy just described above, small p equal to a ratio where the numerator sigma over x small x I, I use the small x for sample values. This is divided by number of values in the sample. The sum of n dichotomous variable taking 1 or 0 has binomial distribution with mean n pi and standard deviation is square root of this. This is mathematics. If you want to avoid mathematics, okay, no problem. As the sample mean has a normal distribution, the mean mu or the mean of the population and variance is sigma square by n. I am introducing symbol variance because so far I have been using standard deviation. The variance is nothing but the squared standard deviation. We deduce that the sample proportion p has a normal distribution with mean phi and standard deviation square root of a ratio, the numerator pi into 1 minus pi, denominator n. This is the thing you have to remember. This is the thing we want you to use in computing values. In actual practice, we do not know the value of the population proportion pi. We shall use sample proportion as an estimate for population proportion. In conducting the test procedure, if you have to use z equal to x bar minus mu divided by sigma by root n, this is what we have been using in testing. Then in the case of testing the proportion, we shall use z equal to p minus p suffix 0 divided by square root of p 0 into 1 minus p 0, this divided by small n. Please note that we are using p 0 in the place of pi. So, p 0 is the value that is proposed by the null hypothesis. Since we cannot get the true value of pi, we shall use the sample proportion as an estimate. That is, our test statistics becomes z equal to p minus p naught divided by the standard error. The procedure for testing x may be used for testing of population proportion. That is the idea we are bringing in here. Checking the applicability of the test procedure, we are told that using the test procedure for sample mean and for population proportion, we can use certain technique or we given the ratio. So, this can be used only when the sample size is very large. How large should it be? A rule to decide is to calculate an interval. You can treat this interval, you can see it. This is very simple to compute because it involves only p sample proportion, and after computing this, check whether this interval is completely contained within the interval 0, 1. We restate the testing procedure for population proportion. Propose a null hypothesis H phi equal to pi suffix 0. Phi suffix 0 is the value proposed. Decide the nature of alternative hypothesis. It could be k phi less than pi 0 or k is pi greater than pi 0 or k pi is not equal to pi 0. Now, if we fix alpha, the level of significance, this is either 0.05 or 0.01. Then decide the critical region, which is according to the type of k, left tail or right tail area or both left right tail areas. So, we have given a figure here. The top one is a normal curve is drawn, and I am considering a alternate hypothesis phi less than p 0, and you can see that the critical region is on left side. The bottom figure, the critical region is the right side, because the alternate hypothesis is a greater than type. In the middle, I have given a diagram where the critical regions on the both side. Here the alternate hypothesis is not equal to type. The test statistic is already given, you can again check it. Now, we compute Z and make a decision on rejecting H or not rejecting it. Solved problems. Problem number 1. A soft drink maker claims the majority of adults prefer his beverage over that of his competitor's brand. He showed the data that of 500 randomly selected adults, 270 preferred his beverage. Determine whether there is sufficient evidence at the 5% level of significance to support the soft drink maker's claim. Solution. We compute the sample proportion small p equal to 270 divided by 500, that is equal to 0.54. Now, I am going to compute a square root of p into 1 minus p by n, that is after imputing the values I get 0.02. Now, we compute the interval 0.54 minus 3 times of 0.02, comma 0.54 plus 3 times 0.02. This turns out to be 0.48, comma 0.60. This is an interval which is completely contained within 0, comma 1. Hence, we can carry out the test for proportion. Now, let us take up the testing part. As the market is expected to be evenly shared by competitors and there are only 2 shareholders, we have the null hypothesis H is phi equal to 0.50. The alternate hypothesis reflects the claim of manufacturer. He claims K is phi greater than 0.50. Please remember, he is claiming that his product is preferred by more adults. Now, we have a right tail test. The critical region for 5% level of significance is 1.645 comma infinity is interval, open interval. The test status is computed as z equal to p minus phi 0 divided by square root of p into 1 minus p by n, and this after putting the values gives you 1.789. This is above 1.645, that is it falls in the critical region. Hence, we reject null hypothesis. The data provides sufficient evidence at the 5% level of significance to conclude that a majority of adults prefer the company's beverage to that of their competitors. Problem number 2. Globally, the proportion of male newborns is 51.46%. A researcher believes that the proportion of boys at birth changes under severe economic conditions. To test his belief, a sample is taken. It is found that of 500 randomly selected new birth records of babies born during a period of economic recession, 52.55% of the newborns were boys. Determine whether there is sufficient evidence at the 10% level of significance to support the researcher's belief. First, compute square root of p into 1 minus p by n. After putting the values, please note that the p is the sample proportion. This turns out to be 0.01. Again, we compute the interval given by the formula p minus 3 and square root of p into 1 minus p by n. The same thing added on the right hand side, p plus 3 times. The value is 0.4955 comma 0.555, an interval, very narrow interval. This clearly contained in the interval 0, comma 1. Thus, validity check is satisfied. We can proceed with the proposed testing procedures. The null hypothesis H equal to 0.5146. This is the world proportion of male boys. The alternate hypothesis K is phi not equal to 0.5146. For alpha equal to 0.10, the critical region is the union of 2 tail areas, namely first interval minus infinity comma minus 1.645 and 1.645 comma infinity. The computed value of test statistics is, after putting the values, we get 1.542. Since this value does not fall on either of tail region, we do not reject the null hypothesis. The claim that the economic condition changes the proportion of male newborns cannot be supported. Now, the key takeaways from this part: we learned the concept of a factor and of its categories. We derived an analogy between mean of a variable and the proportion of a fixed category. We studied how a proposed value for the population proportion can be tested. We solved some numerical examples. Lesson summary: the method of testing procedure in the case of a large sample was undertaken. We understood the logic behind the testing of population mean. We studied how a proposed value for the population proportion can be tested. Some numerical examples were done to understand the test procedure. We have come to the end of the lesson. I hope you have learned something and you will be having the experience of understanding and applying the methods to the real life problems. Thank you.